Right now, at this exact moment, there is a place in our solar system that stayed hidden from human eyes longer than the far side of the moon, longer than the floor of the deepest ocean trench, longer than the surface of Pluto. It is not far away, and it is not faint. It is the top of our own star. We photographed the far side of the moon in the late 1950s. We mapped the volcanoes of Mars. We flew past Pluto and came home with pictures of its ice mountains. And through all of it, the North Pole of the Sun sat unseen, a blank spot on the most important map we have. Only last year did that change. When the first images came down, the scientists who had waited decades for them used a phrase that belongs in an old atlas. Terra incognita, unknown land. But the pictures are not the strange part. The strange part is the question that comes before them, because if you want to know what sits directly above the sun, you first have to answer something much harder. Above according to whom? There is no up in space, no ceiling, no floor, no arrow bolted to the universe telling you which way is high, and yet every map of the solar system you have ever seen has one. The sun in the middle, the planets circling around it, laid out flat on the page like plates on a table, north on top, because that is how we draw things. That picture is not just simplified, it is oriented by an accident of human habit, and once you pull that thread, the whole diagram comes apart. The sun's own pole does not point where the map says it should. The plane of the planets does not line up with the galaxy. The direction we are actually traveling is not any of the directions you would guess. And when you follow the line straight up out of the top of the solar system past everything, you do not find emptiness. You find a hole, a genuine gap in the structure of the Milky Way, sitting almost exactly over our heads. And it may be the luckiest accident in the history of astronomy. 5 months from now, a spacecraft is going to steal momentum from Venus to climb higher above the sun than any machine has managed in a generation. What it sees when it gets there depends on everything we're about to go through. Let us start with the map, and with the mistake buried inside it. The flat picture of the solar system is not wrong, exactly. The planets really do orbit in roughly the same plane, and that plane has a name. It is called the ecliptic. It exists because of how everything here was born. 4.5 billion years ago, there was only a cloud of gas and dust collapsing under its own weight. As it fell inward, it spun faster, the way a skater pulls in her arms, and as it spun faster, it flattened. The solar system is flat because it is the fossil of a spinning cloud, so the flat map is honest about the shape. What it lies about is the orientation. When you draw the solar system with north at the top, you are borrowing a convention from Earth. From our own rotation axis, which we call up because that is where the compass needle leads and because European map makers drew their own hemisphere at the top of the page. That north is entirely ours. The solar system has a different north. The ecliptic has its own pole perpendicular to the sheet the planets ride on, and it does not point at Polaris. It points into Draco, the dragon, a faint winding line of stars few people have ever picked out of the sky. Find that patch of Draco tonight and you are staring straight out of the top of the solar system and it looks no different from anywhere else. That is the first crack in the map. Our up in the solar system's up were never the same direction, and here is where it stops being a matter of convention and becomes a genuine mystery. The sun should be lined up with the planets. It formed from the same cloud and spun up out of the same collapse. Its equator should sit flush with the ecliptic. It does not. The sun's rotation axis is tilted about 7.25 degrees away from the pole of the planetary plane. Our star is leaning, not enough to notice in a photograph, but far enough that astronomers have argued about it for a century because producing that tilt means tipping over an object holding more than 99% of all the mass in the solar system. None of the explanations has won. Some argue the tilt was there from the start, that the cloud was lopsided before the sun ever ignited. Others think a passing star tugged the young disk off kilter while the system was still forming. And in 2016, a team at Caltech proposed something bolder. They suggested the tilt is evidence of an undiscovered planet far beyond Neptune on a long, slow orbit that has been quietly torquing the entire solar system for billions of years. That planet has never been found. The tilt is still there. So already, the question has split into two answers, pointing several degrees apart. The top of the planetary plane and the top of the sun itself are not the same place, which raises the obvious question. How much do we actually know about what that pole looks like? For most of the space age, almost nothing, for a reason that sounds impossible when you first hear it. Getting a spacecraft over the pole of the sun is not merely difficult, it is close to the hardest thing in the solar system. Earth is racing around the sun at roughly 30 kilometers every second, and every rocket that leaves the ground inherits that speed. It is free momentum, and it is why interplanetary travel works at all, but that momentum is locked into the flat plane. To rise above the sun's pole, you have to cancel almost all of it and turn the leftovers into a climb. No rocket ever built can do that, so if you want to go up, you cannot go up. You have to go sideways first, out to something enormous, and let its gravity throw you. That was the plan behind Ulysses, one of the most counterintuitive flight paths ever attempted. It launched on the 6th of October 1990, carried into orbit by the Space Shuttle Discovery. Then, instead of heading toward the Sun, it went the opposite way, all the way to Jupiter. On the 8th of February 1992, Ulysses swung close enough to feel Jupiter's full gravitational grip, and the giant planet flung it clean out of the plane. Not faster toward the Sun, upward. The probe was kicked onto a steep orbit over the solar poles, reaching solar latitudes above 80 degrees. Think about what that required. To look at the top of our own star, we had to fly 500 million miles in the wrong direction and borrow the momentum of Jupiter just to change course. It is the interplanetary equivalent of walking around an entire city block, because you cannot open the door in front of you. And when Ulysses finally arrived over the pole, it could not see a thing. Ulysses carried no cameras. It was built to taste, not to look. Its instruments measured particles, magnetic fields, and radio waves, the physical stuff of the solar wind flowing past its hull. It crossed the sun's north pole in the middle of the 1990s and sent back numbers rather than pictures. And what those numbers said rewrote solar physics. Before Ulysses, the assumption was that the solar wind, the stream of charged particles pouring off the sun, was fairly uniform and that fast gusts were exceptions. Ulysses found the opposite. Over the poles, the wind blew steadily at around 750 kilometers per second. Near the equator, it crawled at closer to 350. The sun was venting a gale from the top and bottom while dribbling a slow breeze around its waist. The polar magnetic field held a surprise, too. It was weaker than the models predicted, which mattered because the poles are where the sun's magnetic cycle gets reset. Ulysses watched that reset from a vantage point nobody had ever occupied, confirming that our star's entire field flips direction roughly every 11 years. It kept working for 18 and a half years, 4 times its planned life, until its nuclear power source faded too far to keep the fuel from freezing in its lines. Contact was lost on the 30th of June, 2009. Ulysses had circled the sun's poles 3 separate times. It told us what the top of our star feels like. It never told us what it looks like. For 16 years afterward, the pictures did not exist. Every image of the sun you have ever seen was taken from near the flat plane of the planets. We were looking at our star edge on forever, like studying a person you only ever meet in profile. Then a European spacecraft called Solar Orbiter started climbing. It launched in February of 2020, using the slow-motion cousin of the Jupiter trick. Rather than one violent shove, it trades momentum with Venus over and over, and each close pass tips the orbit a few more degrees out of the plane. A staircase built out of gravity, and every step takes years. In February of 2025, one of those encounters pushed the spacecraft from around 7.5 degrees of tilt to about 17, roughly the slope of a steep driveway. It does not sound like a triumph, but for the first time, it was enough to see over the edge. Between the 16th and the 24th of March, 2025, Solar Orbiter looked down at the south pole of the sun and took the pictures nobody had ever taken. The pole did not look the way it was supposed to look. Instead of a clean, single polarity covering the polar cap, the way a bar magnet has one clear end, the field was a scramble. Patches of north and south polarity crowded against each other in a tangled mosaic across the same region. Both magnetic directions, at the same pole at the same time. That sounds like a failure of physics until you learn when the observation was made. The sun had just come through the maximum of its 11-year cycle, the point where the global magnetic field turns itself inside out and swaps ends. Solar Orbiter caught the pole mid-flip in the most chaotic phase of a process we had only ever inferred from a distance. We had theories about how the reversal works. Now there was a photograph of it happening. The still images were only the opening move. Over that same stretch of March, the spacecraft did not just capture a snapshot of the polar magnetism. It watched the field move. The outer layer of the sun boils, forming enormous convection cells of rising and sinking gas. On the visible face, we have tracked those cells for decades. Over the poles, nobody ever could. Using the polar cells as markers, researchers measured how magnetism migrates up there and published the result in November of 2025. The field was drifting toward the pole at roughly 10 to 20 meters per second. A walking pace on the surface of a star. That was faster than expected. Measurements from down in the ecliptic had suggested the poleward flow slows almost to a stop at high latitudes. The direct view says otherwise. Polar field strength is the best early warning we have for how violent the next solar cycle will be. Strong fields mean an active cycle, more flares, more storms, more risk to satellites and power grids. Weak ones mean a quiet cycle. If the material feeding those poles moves faster than our models assumed, our forecasts have been resting on a bad guess about the one region we could never check. So we finally look at the top of our star, and the first thing it tells us is that our forecasting was built on a blind spot. Now pull back, because the question was what lies above the sun. Once you leave the solar system, the map does not just bend, it falls apart. Picture that flat disk of planets again, lying level. Now picture the Milky Way. Also a disk, 100,000 light years across, with its own plane and its own definition of flat. Almost every diagram quietly encourages you to assume the two line up, that the solar system lies flat inside the galaxy like a coin on a tabletop. They are not even close. The plane of the planets is tilted roughly 60 degrees to the plane of the galaxy. Our solar system is not a coin lying on the table. It is a coin propped up on its edge, leaning at a steep angle across the grain of the entire Milky Way. Sit with that image, because it changes the shape of everything you thought you knew about this place. As Earth travels around the sun, it is not sliding along the galactic disk. It is cutting across it diagonally, rising above the local star traffic on one side of its orbit and dropping below it on the other. Every orbital diagram you have seen is drawn in a frame with almost nothing to do with the galaxy we live in. And the galaxy has its own up. The North Galactic Pole sits in a small, dim constellation called Coma Berenices, Berenice's hair. Nowhere near Draco, nowhere near Polaris. A third answer to the same simple question. And we have not even asked which direction we are moving. This is where the map really gives up. You would think direction of travel would be simple, but motion only means something relative to something else, and the sun is moving relative to three different things at once. Measured against the nearby stars drifting beside us, the sun is traveling toward a point in Hercules, close to the bright star Vega, at roughly 20 kilometers per second. Astronomers call it the solar apex. Look at Vega on a summer night, and you are looking roughly at where we are headed. Measured against the thin gas we are drifting through, the answer changes. Our solar system is embedded in a wisp of interstellar material, and our motion relative to that gas points somewhere else entirely, over toward Scorpius. That one matters because the heliosphere, the cocoon of solar wind around all of us, is not actually a sphere. Being blown while moving gives it a compressed leading edge that researchers call the nose, and a long streaming tail behind. The nose points wherever the local gas comes from, which is none of the directions we have discussed. Then there's the biggest motion of all. The sun orbits the center of the Milky Way at something like 230 kilometers per second, carrying us towards Cygnus, the swan. One lap takes around 225 million years. The last time the sun sat in this exact spot, dinosaurs had not appeared yet. Three motions, three forward directions, all happening at once, all true, none of them drawn on the poster in your old classroom. And the vertical motion is the one that finally answers our question. The sun does not orbit the galaxy in a flat circle, it bobs. As it sweeps around the galactic center, the gravity of the disk pulls it back toward the midplane whenever it strays. Overshoot, get pulled back, overshoot the other way, get pulled back again. The result is a slow oscillation up through the disk and down through it, on a cycle measured in tens of millions of years. Right now, we are not in the middle. Careful modern measurements put the sun roughly 17 parsecs above the galactic midplane, about 55 light years up. We are above the galaxy's center line, and we are still climbing, which means the line pointing straight up from where we sit is not aimed into the crowded, dusty heart of the disk. It is aimed out, toward the edge, toward the thinning gas at the boundary of everything we call the galaxy. And that is when this story gets genuinely strange. Our solar system does not sit in ordinary interstellar space. It sits inside a cavity. Millions of years ago, a series of massive stars in this neighborhood ended their lives as supernovae. Those explosions shoved the surrounding gas outward and cleared a huge, roughly egg-shaped void in the interstellar medium. Astronomers call it the local bubble, and the sun wandered into it a few million years ago, entirely by chance. The bubble is enormous. Its walls sit hundreds of light years away, averaging something on the order of 550 light years to the dusty boundary. Inside, the gas is thin and hot and nearly transparent. But the shape is what matters, and a three-dimensional map of the local dust, published in 2024, made it clear. The local bubble is not sealed. It is open at the top. Toward galactic north, the cavity does not close off into a wall. It stretches outward and upward until it merges into the space above the disk. The researchers stopped calling it a bubble at all. They called it a chimney. A vent punched through the gas and dust by dying stars, funneling material up and out of the disk into the halo beyond. And we are sitting inside it, under the opening. So here, at last, is a real answer. What is directly above the sun, in the largest sense the word can carry, is a hole in the Milky Way. Not empty, because space never is, but cleared, swept. A corridor of thin material running straight up out of the galaxy, cut by stars that exploded before our species existed. That is not a small detail of local geography. That is the reason we can see the universe at all. Think about what a galaxy looks like from the inside. We live in a disk packed with gas and dust is very good at stopping light. Look along the plane of the Milky Way, and you are staring through thousands of light years of the stuff. Whole regions of our own galaxy are hidden behind it, not because those stars are faint, but because there is too much grit between us and them. Now look up through the chimney, out of the thin part of the disk toward the North Galactic Pole and Coma Berenices. That is the clearest window out of our galaxy we have. Barely any dust, barely any gas, a gap in the curtain pointing almost exactly the way we happen to be drifting. So what do you see through it? Not much, with your eyes. Coma Berenices is famously faint, a scattering of dim stars many people cannot pick out under city lights. Point a telescope through the same window and the emptiness turns out to be a doorway. Roughly 320 million light-years away sits one of the richest concentrations of galaxies in our part of the universe, the Coma Cluster. Over 1,000 galaxies, bound together by gravity, hanging in the dark almost directly over the top of the Milky Way. That cluster is visible because the chimney is open. In almost any other direction, the dust of our own galaxy would have hidden it, which is also why astronomers aim some of their deepest surveys at this patch of sky. And there is a piece of history buried in that cluster that ought to stop you. In the 1930s, an astronomer named Fritz Zwicky measured how those galaxies were moving and found they were orbiting far too fast for the visible matter to hold them together. Something invisible had to be supplying the extra gravity. That observation, made by looking straight up through the hole above our heads, was one of the first serious pieces of evidence for dark matter. We found the missing mass of the universe by looking out of a chimney that supernovae dug for us before there were humans to look. There's one more turn, and it is the one that finally breaks the map for good. Everything we have described rests on a coordinate system. Galactic north, galactic plane, galactic longitude. The International Astronomical Union defined it in 1958 using the best radio measurements of the era, and it has been printed in every textbook and coded into every star catalog since. It was defined to an accuracy of about 1/10 of a degree. That was fine for decades. It is not fine anymore. Modern instruments measure star positions to fractions of a millionth of a degree, and when researchers recalculated where the true perpendicular to the galactic disk lies, they found the official pole is slightly off. Not enough to matter for a diagram, more than enough for precision work. So the direction the entire field of astronomy has been calling up for the better part of 70 years is a rounding error inherited from 1958. That is the honest state of the answer. Above the sun is a direction we invented, measured against a plane we approximated, defined by a committee and quietly corrected later. Which brings us back to right now, and to a date on the calendar. On the 24th of December 2026, 5 months from now, Solar Orbiter passes Venus again. That encounter is not a routine course correction. It tips the orbit from about 17 degrees up to around 24, and formally begins what mission planners call the high latitude phase. Another Venus pass follows in 2028 and another in 2029, climbing toward roughly 33 degrees. Each step buys a steeper look down at the polar caps, and each costs years of patient orbital bookkeeping. The timing could hardly be better. The sun's magnetic field has just finished flipping, so the poles are rebuilding themselves from scratch. Whatever settles in over the next few years determines how stormy the following cycle will be, and recent forecasts suggest those rebuilt fields may come in unusually weak compared to the last several cycles. If that holds, it points toward a quieter sun in the 2030s. If it does not, the models need work. Either way, for the first time in history, we will be watching it happen from above rather than guessing at it from the side. We spent the whole space age unable to look up. That is ending now, in stages. If you want to be there when those first steep polar images come down, and see whether the sun's rebuilt magnetic caps behave the way we predicted, or embarrass the models all over again, stay with the channel and follow along. This is one of the rare stories where the next chapter already has a date on it. So, one last time. What is directly above the sun? Above the plane of the planets, a quiet stretch of Draco with no bright star to mark it. Above the sun itself, a slightly different patch of the same constellation because our star leans about 7¼ degrees, for reasons nobody has proven. Above the galaxy, Coma Berenices, 60 degrees away from the first two answers, in a direction our flat maps never draw. And physically up there, a chimney carved by exploding stars opening onto the halo of the Milky Way, with 1,000 galaxies visible through the gap. 4 answers, 4 directions. All correct. That is the part worth carrying with you. Up is not a property of the universe. It is a habit we brought with us from a planet where things fall down. Space has no top and no bottom, no north wall, no ceiling, and every map that shows one is showing you a decision somebody made rather than a fact somebody found. And yet, the arbitrary direction we happened to call up turned out to be the one direction with a clear view out. A hole above our heads that we did not dig, pointing at galaxies we did not know existed, revealing matter we could not see, from a solar system tilted at a strange angle inside a bubble blown by stars that died long before anyone was here to name them. We are drifting upward through that gap right now, and we will keep drifting for millions of years before the galaxy pulls us back down through the disk. For now, the window is open. Go outside tonight, find that faint smudge of stars, and look straight up through the hole in the galaxy. There is nothing above you, and it is full of everything.